Okay, so welcome to the Design Symposium for the College of Engineering. I'm Professor Brenda Haven, and my awesome students. This is ME 429. It's Propulsion System Preliminary Design, and Sean Berg is the design team lead. He's going to introduce the project. With that, you're on.
All right. Good morning, everyone. We are Aerospace, and this is our final preliminary design presentation. First off, we'd like to acknowledge a few key people: Dr. Brenda Haven, Dr. Mike Fabian, Dr. Matthew Haslam, Dr. Lance Straub, Dr. Jacopo Ciccone, and Dr. Daniel Danley. We'd like to thank them for their continued support and feedback throughout this process. Now I'd like to introduce my team. So as Dr. Brenda Haven said, I am Sean Berg, I'm the design team lead. We have Tori Grant, Lauren Bowman, Tanner Gray, Kurt Chin, and John Huff. And you'll see on the screen here is an outline of what we'll be discussing today throughout this presentation. I will be discussing the introduction of this presentation. So the purpose of this presentation is to present the final decisions and results that were found in Phase 4, as well as present our final preliminary design, and introduce the tasks to be performed in the detailed design. Viper Aerospace was tasked with the design of a propulsion system for a pre-existing unmanned air vehicle. The propulsion system must consist of a ramjet engine as well as a solid rocket motor. We were given some requests for proposal, or RFP, requirements. As you'll see on the screen here are some of the mission requirements. Our system must be capable of a static launch from land or sea. It must be capable of flight at least Mach 1.5 or greater for 250 nautical miles. It must have an operational radius of at least 150 nautical miles. Be capable of at least Mach 2 flight at 30,000 feet, as well as capable of steady level unaccelerated flight, or SLUP, at 45,000 feet. Additionally, we are given some configuration requirements. So, as I stated earlier, we must have a pre-existing air vehicle, which we will be re-engineering with a ramjet, as well as it must have a solid rocket motor. Also, our system must be capable of carrying at least 50 pounds of payload. This payload may include either reconnaissance equipment, supplies, or a warhead. As you'll see on the screen here, this is a general mission profile of what our system will be able to do. So notice the solid rocket motor will propel the entire system up to a desired altitude Mach number, where it will then jettison. The ramjet will then take over as the primary propulsion system for the remainder of the mission. After the mission is completed, the ramjet will turn off, and the air vehicle will glide to reduce speed and altitude, where the recovery system will then be deployed. Some quick basics of what a ramjet is. A ramjet is a jet engine which has no rotating machinery. It uses rammed air to produce thrust. It cannot operate at static or stationary positions, which is why we need the solid rocket motor to propel it up to supersonic speeds. I'll now pass it off to Tori Grant, who will be discussing airframe selection.
Thank you, Sean. So initially, Viper Aerospace looked at different air vehicles, including surface-to-air missiles, cruise missiles, and unmanned fighter jets. From there, we narrowed it down to two different air vehicles: the Regulus II, which is a cruise missile, and the Beaumont, which is a surface-to-air missile. Due to the fact that the Regulus II had met all the RFP requirements and mission criteria, and the airframe of the Regulus II was structurally capable of reaching speeds of Mach 2, the Regulus II was chosen as the pre-existing air vehicle for our project. There's also a vast amount of technical data that was given by the Regulus II, including aerodynamic data such as coefficients of lift and drag, also schematics of the air vehicle, including dimensions of the whole air vehicle, and physical characteristics such as the length of the air vehicle, the weight, and the type of ramjet, the type of engine, and rocket booster that the air vehicle used. I'll also be going over the design of the solid rocket motor, or SRM for short. So the team decided on design choices that the SRM needed to do to assist the air vehicle in its missions. The first being that the SRM had to propel the air vehicle to a speed of Mach 1.7 and then get the air vehicle to an altitude of 15,000 feet. The total burn time of the SRM will be 10 seconds. Here is general information on the SRM. The total length of the SRM is 22.25 feet with a case length of 20.75 feet and a nozzle length of 1.5 feet. The diameter of the case is 2 feet, about 2 feet, and the diameter of the nozzle is 1 foot. The expansion ratio, or the exit area, or the throat area, was chosen to be 6.5, which would optimize the thrust at 10,000 feet, which is about two-thirds the way of the SRM. We also picked a 15-degree conical nozzle for the SRM. A 15-degree conical nozzle means that the nozzle itself is 15 degrees from the center line. A 15-degree conical nozzle is typical for SRMs that are used, and it also gives the best performance for the nozzle. The throw area for the nozzle is 0.221 feet squared, and the exit area of the nozzle is 1.41 feet squared. We also initially looked at 4 different propellants and then narrowed those down to 2, those being TPH-3340 and TPH-1202. The other ones were excluded from this due to their height, their not being cost efficient, and their burn rates were too high. As you see from this graph, it shows the characteristics of both propellants that were chosen. From there, we looked at two key factors, including the densities and the price. Although the density is 2.5 pounds per cubic foot less than that of the TPH-1202, this would adequately end weight since the propellant will be 20 feet long. Price was also a big factor. As you can see, the TPH-3340 was about 6 times less the price than that of TPH-1202 due to the fact that TPH-1202 contains a chemical called HMX, which is a high explosive, highly expensive chemical, which makes the price of this one much more than that of the TPH-3340. Because of this, the TPH-3340 was chosen as the propellant for the SRM. So we chose a single circular bore for SRM propellant, with an inner radius of 4 inches and an outer radius of 10 inches. With a single circular bore, this would produce a progressive thrust throughout the entirety of the SRM's mission. A progressive thrust means that the thrust increases over time. The calculated maximum thrust at the end of the SRM's burn is 310,000 pounds of thrust. This is the amount of thrust needed to get the air vehicle to Mach 1.7 and to an altitude of 15,000 feet. From this graph, you can see the amount of thrust produced by the SRM at each time interval of its burn. I'll now pass on to Warren Billman with SRM material selection.
Thank you, Tori. So when designing our SRM, Viper Aerospace needed to choose materials. We began with a case material. We limited this to aluminums as this is needed to be cost efficient because SRMs are not reusable. You will need a new SRM for every mission attempted. For the case material, we were worried about the temperatures and pressures that it would experience from combustion. The expected temperature is about 1 KSI. With these things in mind, we are selecting aluminum 2014 as our SRM case material. From there, we moved on to case insulation material. The case insulation material is needed to protect this metal from the hot temperatures of combustion. The temperatures of combustion are expected to be about 6,100 degrees Rankine, which is well above the melting point of the aluminum that we chose. We also needed to choose a cost-effective material as this will go the entire length of the case, which as Tori stated previously is over 20 feet. For these reasons, Viper Aerospace has picked graphite phenolic as our case insulation material. We then moved on to a nozzle material selection. The nozzle will experience high temperatures. The gas will be exceeding 4,300 degrees Rankine. For these design parameters, Viper Aerospace has chosen aluminum 6061 as the nozzle material. We then chose a nozzle insulation to protect from these high temperatures. One of the most important criteria for the nozzle insulation was the erosion rate. We wanted to maintain a relatively stable area ratio of 6.5. So over the entire burn, the amount that this material will erode is about 0.04 inches over the 10 seconds. For these reasons, Viper Aerospace has picked 3D carbon-carbon as their nozzle insulation material. This is a cutaway of the solid rocket motor. This is to show you the scale as well as the layout of the solid rocket motor. Here you can see the single circular bore, the case insulation, the nozzle insulation, and the igniter. The igniter that Viper Aerospace has chosen is the Pyrogen igniter. This is the industry standard as it is reliable, safe, and easy to use. How a Pyrogen igniter works is that an electric pulse is sent through the igniter leads. This pulse ignites the ignition powder. As this ignition powder burns, it breaks through the burst diaphragm, and that propellant is sent into the bore, igniting the main propellant of the solid rocket motor. This concludes the main points for the solid rocket motor. I'll now pass it over to Sean Berg, and he will begin talking about the ramjet engine design with the engine design point.
Thank you, Lauren. So for the reference point, for the ramjet engine, we chose it to be flight Mach number of 2 at 30,000 feet, as well as a mass flow of 169 pounds mass per second. This was chosen after many iterations through the constraint analysis, as well as the mission analysis. We had some design point choices. So the key things to see on here are that we chose a level 4 technology. This means this is technology that is current from 2005 onwards. The key values to pay attention to up here are the combustor efficiency, which we chose to be 0.99. This efficiency is that of a afterburner, because our ramjet will be operating similarly to an afterburner. Additionally, we chose a combustor temperature of 3,600 degrees Franken and installation loss of 0.06. This value will be further refined within the ramjet engine component design. So for the different missions, we have air vehicle capacity. So for the reconnaissance mission, we chose a payload of 50 pounds, which is the minimum payload as stated in the RFP, leaving us with approximately 9,976 pounds of fuel. For the supply drop mission, we chose a payload of 250 pounds, leaving us with approximately 9,726 pounds of fuel. And then for the terminal mission, we chose a warhead weighing 2,400 pounds, leaving us with approximately 7,573 pounds of fuel. Here is an example of one of our missions. More specifically, this is the reconnaissance mission. So as you'll see, this mission for the ramjet begins right after the jettison of the solid rocket motor. It then takes approximately 690 nautical miles for the ramjet to complete its portion of the mission, and uses approximately, it takes about 36 minutes to complete the mission, and uses approximately 9,666 pounds of fuel. This mission ends when the ramjet turns off and the recovery system is deployed. I'll now hand it off to Tanner Gray, who will be discussing the inlet and diffuser design.
Thank you, Sean. Okay, so to begin, we have the inlet design point, which will be at the max corrected mass flow, which is at the free stream Mach number of Mach 1.8 and an altitude of 15,000 feet. That gives us a corrected mass flow of roughly 90 pounds mass per second and a free stream area of roughly 2.6 feet squared. For the ramp angles, we decided to optimize for Mach 2.0 since that is the highest Mach number we will be traveling. So we chose the ramp angles of 14 degrees and 8 degrees, totaling total angle of 22 degrees. This will have a pressure recovery of roughly 95%. So for the inlet, with these values in hand, we were able to calculate the area of 2 feet squared, and the length of the ramps are roughly 1.7 feet, which gets us a compression ratio of 7.8 and a minimum installation loss of 1.47%. For the ducts, the length will be roughly 14.2 feet with an offset height of roughly 2.7 feet. This is to allow the air to get to the center line of the engine and the main body of the airframe. And there are two main reasons for the long length of the duct. The first one is to try and best to match the original Rigorous 2's inlet position with the J79, and to allow a offset height to length ratio of no more than 0.2. So, and the connector is just, the main purpose is to transform the geometry from a square to a circle to attach to the diffuser, and this will be done over a length of roughly 4 feet. So now for the diffuser, it must be designed to the max dynamic pressure at Mach 1.8 and 15,000 feet, which gives us a mass flow of air, again, of 240 pounds mass per second, and a mass flow of fuel of 12.09 pounds mass per second. We also have the area of the diffuser entrance will be 2 feet squared, which is the same as the inlet, and the diffuser exit will be roughly 5.8 feet squared. The Mach number at the diffuser entrance will be 0.8 once again after the 0.8, the same as the inlet Mach number, and it will slow the flow down to Mach 0.2 going into the combustor. So for the dimensions of the diffuser, the length will be the same as the exit diameter at 2.73 feet, and this gives us an area ratio of 2.9 feet, or 2.9, and the pressure loss across this diffuser is 13.4%, and this is just a simple dump diffuser, which is why the length equals the exit diameter. So for component materials, since none of these materials will be experiencing more than 800 degrees Rankine of an air temp, we decided to go with aluminum 6061 for all of them because of its high melting point of 1500 Rankine, which gives us a large safety margin. Now I'll move on to the ramjet combustor. So the design point of the combustor is also the same as the diffuser at the max dynamic pressure at Mach 1.5 or 1.8 and 15,000 feet. The mass flow of air is roughly 240.45 pounds mass per second, and the mass flow of fuel is 12.09 pounds mass per second. The area at the combustor entrance is the same as the diffuser exit of 5.8 feet squared roughly, and the Mach number going into the diffuser is 0.2. So for the spray rings, they will inject the fuel perpendicularly into the airstream, and they will place exactly 1 inch after the diffuser exit. They will be designed to pass 12.25 pounds mass per second of fuel to allow for any possible errors that could be in the fuel flow rate previously calculated. And there will also be 12 inches from the spray rings to the flame holders to allow for proper mixing. So for the flame holders, we chose a simple V-gutter design, and we chose 2 of them because as you increase the number of V-gutters, the complexity goes up, plus the cost of manufacturing also goes up. And even though the combustor would be shortened, length was not a major constraint to the design of the combustor. So we decided we'd go with just 2 flame holders. The outer V will be a diameter of roughly 2 feet, and the inner V will have a rough diameter of 1 foot. The double angle, which is through the center line of each of the V's, will be 30 degrees. The length of the V will be 0.51, and the mixing transition point will be roughly 0.629 feet, which allows for a stable flame in the combustion chamber. So for the combustor liner, we have the length set to 3.33 feet, to allow for roughly 1.7 feet for the proper combustion to take place after the flame holders, and this will have a diameter of 2.73 feet. And as you can see, there will be cooling holes within the combustor liner to help keep the material cool. So for component materials, the spray ring will be titanium 6AL-4V. This is because though the spray ring is not within the flame area of the combustion chamber, we still want it to be properly capable of supporting the mass flow of the fuel. For the flame holders, we chose Haynes 188 because though they also aren't in line with they aren't within the combustion area, they still must withstand the high temperatures that are very near it. So, and Haynes 188 was deemed appropriate for the protection of the flame holders. So for the combustor liner, we chose a C-129Y, which is a niobium style of material, which though is extremely high temperature resistant. It is not as strong against oxidation or corrosion, so we will use a silicide or a alumina coating to protect it. And now I'll pass it off to Kirk Chen for the ramjet nozzle design.
Thank you, Tanner. Okay. So for the ramjet nozzle, the idea is to raise the velocity of the flow to supersonic conditions while minimizing total pressure losses. During the course of Phase 4, Aerospace looked at the critical mission legs that will be required for the nozzle to perform. These include the acceleration, climb legs, 1.5 G turn, and the design cruise point of Mach 2 at 30,000 feet. These were all set at 100% throttle setting. The A9 over A8 is the expansion ratio that was calculated using Manley's perf software. These values seen on the last column are for a perfectly expanded nozzle. For all these missions, the operational range, the operational altitude would be from 15,000 feet to 45,000 feet, and the range of the Mach numbers was from 1.7 to Mach 2. Therefore, the overall average of the error ratios was rather minimal. Therefore, a fixed simple geometry nozzle was chosen to be designed for the ramjet nozzle. The average of these error ratios was 1.47, and this was rounded up to 1.5. At the start of the ramjet nozzle design, we were required to choose two angles: the angle of converging for the converging section and the angle for the diverging section. These were 15 degrees and 12 degrees respectively. These angles were chosen because length was initially of concern. However, this would be iterated further given more time. Additionally, the hand calculations were performed with two main assumptions, the first being one-dimensional flow and the second being an adiabatic process. To aid in simulating a more realistic model, three design parameters had to be chosen. These include the discharge, angularity, and velocity coefficients, and the values are shown above and the last column. For nozzle performance, this was calculated. These were performed with the hand calculations, and the F actual is based off our hand calculation, while the F reference is the ideal thrust that is calculated, again using the perf software. The worst performance is at the acceleration leg of 0.962. With these numbers, we would use these to go back to the mission analysis and see if how much more fuel will be required to perform these legs. To validate our hand calculations, we used a computational fluid dynamics model. This was created using ANSYS Fluent. The model was created to simulate supersonic flows, and the average exit pressure, average temperature was calculated as well. The average exit velocity was calculated to be 4,201 feet per second, and all three of these calculations had a very minimal standard deviation. Therefore, a one-dimensional assumption was valid. Finally, this is the nozzle dimensions as follows. The nozzle entrance diameter would be 2.73 feet, exactly the same as the combustor exit. The nozzle throat area is going to be 2.54 feet, and the exit diameter would be 3.12 feet. As there is no turbine as a conventional jet engine, the nozzle will be taking the brunt of the exit temperature from the combustor. So to validate the feasibility of the nozzle, a structural thermal analysis was performed in static thermal and static structural in ANSYS workbench. The maximum temperature calculated was approximately 3,489 rankines. Similarly, with these calculations, a super alloy material was required to be chosen to manufacture the nozzle. materials shown above were chosen based off of their high melting point and max operational temperature of 2,460 rankines. The materials are Haynes 188, Hastelloy S, and Hastelloy X. Haynes 188 was chosen because of its availability and also its thermal conductivity at 2,000 degrees Fahrenheit. This material was applied in our model in ANSYS static structural, and the radial deformation was calculated by taking the magnitude of the Y and Z components and averaging them. The result is the increase in entrance area, the choke point, and the nozzle exit area. The overall expansion ratio increased by a 0.59%. These values would be taken back to the original nozzle design, and the nozzle performance would be iterated accordingly. Finally, this is the nozzle axial expansion. This is in the X component of the nozzle. It's a maximum increase of 0.273 inches. Similarly, this would be iterated back in the original nozzle dimensions. This concludes the ramjet phase design decisions, and now I'll pass it on to John for recovery systems.
So one of our mission requirements was that for our non-terminal missions, we have to be able to recover our aircraft reusability. We looked at several different options, including conventional landing, glide landing, and a reverse JADA landing. The issue with the conventional and glide landing is because we're operating a ramjet, we cannot throttle down to low enough speeds to do a safe landing, and also our approach speed would be in excess of 170 knots. So we selected the parachute landing as a recovery system. So the way this landing will work is we'll shut off the engine about 45,000 feet and 10 miles from the landing site. We will glide to decrease speed and altitude, and then at about 30,000 feet, we'll transition to a ballistic attitude, which will be just above the landing site. And then at the altitude, that trajectory, we'll deploy the parachute and then descend vertically to the ground, where we will land on inflatable air cushions, which will allow us to either marine or terrestrial landing. And then this system is designed for 20,000 pounds, which is our maximum weight immediately after the rocket is jettisoned. So our trajectory consists of a 19-degree descent, which is about 2,200 feet per mile. And then we will do the 3G pull-up maneuver and transition to our vertical trajectory. And at the top of that trajectory, we'll deploy parachutes and descend. So for our parachutes, we decided to use the G11 Bravo parachute, which is the standard Army and Air Force cargo parachutes. It's been used for many years, combat proven. Each parachute assembly weighs about 250 pounds, so for a total weight of 1,000 pounds. These will deploy just after free fall begins out of disposable blast doors on top of the missile. A drogue chute will pull out the main parachute, and then it will descend, and then immediately upon touchdown, the parachutes are released to prevent dragging or tipping. So in order for us to land, both on land and sea, we decided to use inflatable airbags similar to what they use on the Apollo space capsules. These will, on terrestrial landing, they'll provide cushion, and then on marine landing, they'll provide flotation to keep the entire aircraft out of water. Since these are typically custom designed, there are no commercially available options for us to use, so we had to design our own airbags. We decided to use polyurethane coated ripstop nylon, which is the common material used for that. And from there, we did our volume and then fabric calculations, decide how big the airbags need to be, and how much material is needed. So in order to inflate them, we looked at blowers and compressed air. The issue with using a blower is that we don't have any turbo machinery to power them. So we decided to use a compressed air tank, which uses a small battery to open the valve. For our air tanks, we decided to use a 5,500 PSI air tank, carbon fiber bottle. These are the same air tanks you see firefighters wearing. These offer the smallest total volume and the lightest system weight. And each airbag will need 2 air tanks to inflate. And then the airbags will inflate about 1,000 feet above the surface, which will allow for them to fully inflate without any negative effects from overexpansion due to altitude. This image here shows the parachutes when fully deployed. There'll be, once again, 4 parachutes. 2 will deploy out the front half of the aircraft, and 2 will deploy out the rear of the aircraft. Each parachute is 100-foot nylon, 100-foot diameter nylon canopy. And this image shows the inflatable airbags. The airbags will be stored in the same positions as the original landing gears of this aircraft, and each airbag is about 10 foot long with 5-foot diameter. Now that we have all components, we can talk about our assembly. So we have 3 options for our payload. The first one is the explosive warhead, which is 2,400 pounds of tritonol, which is the standard Air Force bomb explosive. We then have the cargo box, which can carry up to 250 pounds, and a reconnaissance camera, which weighs 50 pounds. Now these 3 components here will be on every flight. We have 3 fuel tanks, which can carry up to 10,000 pounds of fuel. We'll have 4 of the G11 broad parachutes, which each weigh 250 pounds, and 3 of the airbag assemblies, which each weigh 66 pounds. Each assembly includes the 2 compressed air tanks as well as the folded cloth. The ramjet itself, the entire engine, including the inlet nozzle, weighs about 1,500 pounds. It's 28 feet long with a maximum diameter of 3 feet. This image here shows our current arrangement. The recon camera will be placed in the nose cone of the aircraft. The 4 G11 broad parachutes will be positioned on the top of the aircraft, 2 in the front, 2 in the rear. The cargo box will be positioned in the fuselage in the front half. The 2,400 pound tritonol warhead will be positioned in the center of the aircraft. And the 3 fuel tanks will be dispersed for equal weight distribution. And then flotation assemblies will be placed in the landing gear wells, 1 in the front and 2 in the rear. With this current assembly, this puts our center mass over the wings, which gives us excellent balance and maneuverability. Now, this image here shows our aircraft with the solid rocket motor attached. The solid rocket motor will jettison immediately after it's spent on takeoff. So with all these components together, we present you the X-57. So overall, the X-57 has a total length of 56.5 feet, a wingspan of 19.8 feet, and a total height of 9.9 feet. Depending on which mission and configuration we're using, it can weigh anywhere between 18 and 20,000 pounds. The solid rocket motor weighs 10,300 pounds for a total takeoff weight of about 30,000 pounds. I'll now transition to Warren Bowman, who will talk about our plans for detailed design.
Thank you, John. Viper Aerospace has decided that for detailed design, we would like to construct a combustor with variable flame holder positions. This has been deemed to be a valuable project, as we will be able to measure the variation in combustor performance due to these flame holder positions. The team will be able to analyze when stable combustion occurs based on the different positions. These are the resources available to the team for detailed design. We have access to the blower, which is in the propulsion lab. We also have a test rig in the propulsion lab. We will determine if this is adequate for our testing. If it is not, we will design and build a new test rig. Total, we have $1,000 to spend on materials. Here's a preliminary bill of materials for detailed design. We are looking at purchasing Inconel for the combustor liner. It will cost about $133 as scaled for the mass flow rate of the blower. We would also like carbon steel for the casing of the combustor. This will cost about $50, and we would like to make the flame holders themselves out of brass, costing about $90, for a total of $273. This does not include any manufacturing costs that the team will experience, and it is a rough estimate based on previous detailed design projects. I will now pass it to Sean Berg to conclude this presentation.
Thank you, Lauren. So in order to gauge the success of our design, we analyzed whether or not our design met the RFP requirements. So as you see here, for the mission requirements to stay in the RFP, our system either met or exceeded all the requirements. It can be launched from a static position. It can fly at a Mach number of at least 1.5 for 250 nautical miles. It has an operational radius of at least 150 nautical miles. It can fly at a Mach number of 2 at 30,000 feet, and it is capable of steady, level, unaccelerated flight at 45,000 feet. Additionally, for the configuration requirements, We did choose a pre-existing air vehicle to re-engine with the ramjet, which was Regulus 2. We designed the ramjet to maximize our missions. Excuse me. We use a solid rocket motor, and each of our missions, or the system is capable of carrying at least 50 pounds of payload. Viper Aerospace came up with some recommendations for our design. First off, we have the solid rocket motor design. This would be to maximize the performance of the rocket for the required operation of the air vehicle and the ramjet. Next, we have performed screech liner calculations. These calculations would assist in the limitation of acoustic instabilities within the combustor, as well as assist with cooling. Next, we have developed a design for regenerative cooling for the ramjet nozzle. This would assist in, obviously, the cooling of the nozzle, and thus cut down on the deformation of the nozzle. Next, we have performed structural and fluid dynamic analysis. This would be analysis of the different components within the ramjet and the rocket in order to analyze the different stresses put on them due to the high temperatures and pressures, and make sure that they don't fail due to those. Next, we have analyzed heat transfer of the combustor liner and the nozzle. Again, this would be to assist in the cooling and make sure that they do not deform too much to where they hinder the performance of our engine. Lastly, we have research auxiliary power units. These power units would be to give electricity to either navigational systems, the reconnaissance equipment, sensors, fuel injection, or other systems on board that require electricity. Here is a graph of our predicted hours versus our actual hours. As you'll see in the black boxes is our actual hours, and the red triangles are the predicted hours. As of 7 o'clock this morning, we're at 111% of the predicted hours. Here are our references. Thank you. I would now like to open up the floor to any questions. I can't reach that far.
Yeah, no, let me kick off. Can somebody jump to, what is it, I think it's slide 72. Let's start with, I think it's 72. Yeah, 72 I think it is. Yeah, 72. Okay, you guys are modifying a Regulus system, and it had J79 in, is that right?
Yes,
You guys
yes.
had J79.
Yes.
Early in your presentation, you should have done a stack probably of what the original looks like and what you're proposing, because it helps us know packaging. I mean, so that when you guys mention wheel wells, things are going, it's like, okay, get that.
Gotcha.
So it would really help your story to show you're still in the same profile, you're still following the same thing. And some of these weird links that you guys are very comfortable with the links of different things. It doesn't mean diddly squat to me because I don't have a context.
Right.
And that will help you with your context of why this long duct with a high subsonic Mach number? Why, you see what I mean? That will help your story a lot.
Right.
Okay, so when you're pitching something, help sell early. Okay, so that's that. Your general mission profile chart, what is that, chart 8 or 9? I guess it's 9. Or 9. Okay, the booster takes you to what, like 15,000 feet?
Yes.
So you're flat line in there, so it doesn't tell the whole story, you know. That's because I'm looking at it going, it's early in the presentation. You say the rocket's going to get you to the flight condition, and it's like, wow, that's really high if you're doing some of these RP things. Okay, so what is, you know, and I don't know how to draw it right, but there's the brake line helps, but you could have multiple climb. The odds are you're climbing on ramjet quite a bit right after boost, so that would help you.
Okay.
Go to, what is it, 15. Okay, I'm reading that the case is 2 feet and the nozzle diameter is 1 foot. And I look at the picture and the two diameters look the same. But if I go back to slide 74, see how the nozzle's way smaller than the case? The exit diameter of the nozzle in that picture. Now go back to 9. See the difference? See
Yes, the difference.
yeah. See the difference? See what? So I'm trying to connect things and you got disconnects. So that's an obvious one that jumped at me. Let me see. Heat transfer analysis. Did you guys you guys do some heat transfer analysis on the solid rocket motor, nozzle? I know you were going carbon-carbon, trying to help, because 50% of solid rocket failures are nozzle failures. Did you do some heat transfer analysis, or you just assume carbon-carbon's gonna do what you need?
We kind of assume the carbon will do what we need. I don't know if Tori or Lauren has anything to add.
That would be from our recommendation slide, that we would go back and iterate that.
I saw that at the very end.
Yeah.
That's what, I'm making comments as I go along. On slide 31, you mentioned the 10,000 pounds. I have no idea what the original Regulus fuel volume was.
Okay.
John got to it later of, hey, I've got 10,000 pounds worth. But when you're doing this, it would really help to say, later we will show that we meet these max volumes or whatever.
Okay.
Because as I'm looking at it, I'm going, boy, I wonder if that's a lot or a little on an existing system.
Gotcha.
Okay. Slide, I'm trying to go fast, 36 or 30, no, 38. 38. Any concerns with flow transition from square to round? You look at that, have other people done that? What's your basis of all is well?
Passes the 10.
Because the change in the geometry, I did my best to keep it as gentle as possible,
Okay.
in the hope that it will remain axial.
And your length looks pretty good, so I
Yeah.
think you're probably okay, but it's just one of those
Yeah.
things.
It'd be another thing to analyze too, or if we'd have to correct the flow.
It's kind of how we had the fluid dynamics also in the analysis within the recommendations.
All right, how about 46? Any choice on hole size with acoustics?
No. Again, that's in our recommendations. Stuff that we put in there because we knew we would need it for cooling and for acoustics, obviously, but it's one of the things.
It's a pretty fast turn to get some feel for that, because you got a volume, so you can figure out what the natural frequencies are of that. That's good. Okay, you mentioned heat load for that nozzle question, so I'll get rid of that. Like that. Okay. I think that's it for me, main ones. Technically looked very clean.
Thank you.
Anybody else? Next.
I got, just going back off of the first thing that Dr. Fagan was saying, in comparison to the original, I guess what I would be wondering predominantly right off the line is why would I want to buy this? And so like a comparison of the actual increase in capabilities from what you started with, because it looked like it was a redesign of the capabilities and increased range and everything else. So a comparison of what exactly you're getting from when you start to what the new version is capable of. And then, yeah, so I guess, do you have that, or?
We don't, I don't know if we have it in the appendix, but, well, John has all the information.
So the original Regulus 2 was cruise missile. It had actually similar range to what we had, but that was its sole purpose, was to fly and crash. Ours has 3 missions, which are the reconnaissance mission, supply drop mission, and it can also do a terminal mission if necessary. And then our biggest requirement that we had was to take existing turbojet engine and replace it with a ramjet engine to make it cheaper and lighter, pretty much.
So originally it had no capability of recovery.
No.
No.
Their test models had landing gears in them, but that was just purely for testing. The actual operational model, one-way trip. So.
Did you do any analysis on the tanks and being able to handle like because you're using air tanks, right, to detonate or to inflate the parachutes, about them being able to stand up to the thermal environment of that, and whether or not you have a tank rupture or anything like that in those lines?
Thermally, no. These are we're using firefighting air tanks, which are meant for extremely high temperatures, up to 800-900 degrees, as well as excess pressures. They have factor save of 1.5 built in. So.
And that's in our recommendations for all the heat transfer as well as thermal stresses. So I mean, it's stuff that we need to look into.
Okay, I guess probably my other question thermally was relating to the motor itself, between the air friction, between the internal combustion, and then like radiation coming from the flame out the back. Would the aluminum be able to stand up to all of those combined? That's kind of a question I had, but again, that might be well outside. Oh, there was on slide. sub 9 and A sub 8. What are the 8 and the 9?
And so we're the curb.
Okay, so the A sub 9 is the exit area, and then A sub 8 is the choke area, the nozzle throat area, sorry.
Okay. Is there any particular reason you went with 8 and 9 instead of A and E, or T and E?
The D, sorry, could you say?
Just as far as like, because it's the exit, the area at the exit and the area at the throat, typically it's like A sub T and A sub E.
Oh, I think there's a difference between ramjet culture. Yes, culture. The cultures are different, so.
Okay.
Yeah. So.
Okay, sorry, I was not aware.
Yeah, conventionally for like a turbojet engine, we have stations 1 through 9, and at the throat is 8, and at the nozzle exit is 9. So from what we learned, we kind of kept that consistent for us.
Okay, so that is pretty standard then.
It is a standard numbering of the station. Yeah.
Didn't know that, thank you. And, just for the parachutes was my last one. You said the drag chute and then the full chute. Now, what is the drag chute? Is that like a partial opening of the chute? Or?
Drogue chute is a small parachute that pulls the main parachute out of packaging.
Okay.
So that's all its job is to pull the whole thing out, because you have a 100-foot diameter piece of nylon, you need something kind of help that pull itself out.
Okay.
So that's standard, including the packaging of that parachute assembly.
Okay. And did you check to make sure that that parachute, how fast is it going when the parachute's deployed?
The parachutes, this is going to be just after free fall begins, so it's going to be a very slow initial speed. So that's good.
Also, you mentioned that it was 100-foot diameter nylon. Probably just would have been nice to throw that in somewhere visually. I didn't see it written anywhere. I just heard you say it was 100 foot. And I think that's it for me.
Okay, thank you.
Thank you, Alex. So first off, I agree with what Dr. Fabian said. It seems like you guys did a pretty good comprehensive book. Ramjets aren't easy. There's still looking at it. So just throw that out there. I got a lot of just little questions about certain choices, maybe just because I didn't understand. So first off, it was a requirement to use a ramjet, right?
Yes.
Okay, just wanted to make sure. Okay, for SRM, that's slide 15. That's the SRM dimensions. I think Tori said that you'd optimize to 10,000 feet. I was just wondering why you chose 10,000.
Well, since we're going to 15,000 feet is where the mark of jettison, for the optimal pressure, we want that to be 2/3 of the way up to altitude, so it would be at 10,000 feet.
Okay. Yeah, it's just, I remember hearing that number and I couldn't remember why. For your SRM, another question I think you might have said, and I just didn't hear it. What type of burner did you say you were using for your grain? Is it just an end burner? Is it wagon wheel? What are you using?
It's a circular burn.
Okay. Okay. Yeah, sorry, I may have just not heard. For slide 22, did you consider materials other than aluminum?
Lauren, would you like to take this one?
We did not. We went with aluminums because this part cannot be reused, so we wanted to keep it very cost effective.
Okay. I thought it was kind of strange that all I saw was aluminum. Okay. I answered that. Slide 30. So, who was the presenter at this point? Sean, I think. I made a comment similar to an afterburner.
Yes.
What do you mean by that?
Since our ramjet, essentially it has air come in and it heats it up and sends out the nozzle, which is kind of, I guess, similar to an afterburner where it comes in and fuel is added and accelerates the fuel or the air to that. So it's operating similarly to an afterburner. I don't know if Tanner wants to expand on that at all, or
That explains it pretty well, unless you have any additional questions on that.
Yeah, I just asked because it's not inaccurate. It was just, it seemed kind of unusual since, afterburners usually add on to a turbine. And
Right.
your flight envelope is kind of the transition from when a turbine becomes less efficient than a ramjet, kind of. And that's why I was making sure using a ramjet was a requirement. So it was just an unusual comment I thought. For slide 31. So the first two payloads kind of in the same order of magnitude. And your third one is huge.
Yeah.
I was just kind of wondering why you have this massive scaling up in payloads, I guess. I mean, why should I guess, as a customer, why should I buy the system for reconnaissance if it can only carry 50 pounds, but it can carry a 2,000-pound warhead? It just seemed kind of strange.
Yeah, Sean would like to assist in this for
So the original Regulus had nuclear warhead on it, which weighed that much. So for a deterrent mission, we figured it's a one-way trip. We're not going to need all the extra equipment. Might as well put the biggest thing possible. If we're doing a purely reconnaissance mission, that weight can be transitioned to extra reconnaissance equipment. However, we'll have less fuel capacity. So that's why we stuck with the minimum required weight, so we could have the most fuel capacity for range for the reconnaissance mission.
Okay. Okay, that's exactly what you need to say, because I'm kind of sitting here wondering why shouldn't I use a smaller system that can still carry that 50 pounds? And maybe it's not a ramjet, but it can still get up past Mach 1. So just make sure you state it for that reason. Also, just a quick thought on warheads, because I think you were talking, I can't remember what the slide is off the front. You're talking about how you're going to use all 2,000 pounds as explosive. Is that the case?
2,400 pounds. Or, yes. At least that's the standard Trident bomb or something like that we had found the Air Force uses.
Okay. Okay.
We didn't look too deeply into the explosive part. It was just a requirement that we had to have it. So we didn't look into detonation and all that fancy stuff.
No, I didn't have a problem with that. It's just it seemed like an awful lot of explosives.
Yeah, we just went with a standard, a big standard bomb.
So just a thought. I was just wondering if you looked into like casings or things like that. It did seem outside of the scope. I was just curious.
Yeah.
Talk about that. For slide 47. Sorry, I'm full of easy questions today. I think muster lining. You said you're going to put a coating on it. Are you worried about getting sloughed off?
And we have not analyzed that part, so I'm not quite sure. So it'd be something that we'd have to look further into for TBCs and this sort.
Because I was just sitting there thinking, well, coating's great. It will increase your life, but if it comes off and it burns through, that doesn't mean a thing.
And well, also when I found this material, it suggested either silicide or aluminum coating too. So I'm assuming they should have tested it to prove that it was appropriate for this material.
Okay.
So,
Yeah. Let's get the validation. Around slide 51, just kind of in this area, or actually I think it's more like 60. Sorry, that's 61. When you guys were going through the section talking about it, I thought it would be really helpful if you just had a quick matrix that showed these are recovery methods considered because you said them. But I think if you had a visual aid for that, that would help me because I was just sitting here thinking, okay, why'd you use these methods? So just that would have really helped, I think, your presentation for this section. So just quick thought. Also for inflation, that's 65, I think. You said you used blower or compressed air. Did you consider chemical, like an airbag for a car?
We did not really. We're just trying. One of the things was keep it low cost, so that helps with that.
Okay. I guess I was just wondering if maybe you could take some system from a car, scale it up, throw it in, and it'd just be maybe a bit easier.
And there's also no need for such a violent expansion in our case either.
That is true. Okay. Just curious if you consider it.
Yes, one question for, it's more of an introductory one, but J79 is a relatively heavy engine. I'm not sure what its fuel consumption is, but did you take a look at all at the weight of the J79 plus the weight of the fuel to complete a mission versus the weight of the ramjet and its fuel requirement to complete a mission?
We looked at the original Regulus 2. John can correct me if I'm wrong. It was at 22,000 pounds with the J79 fully loaded.
And the J79 itself weighs roughly 3,500 pounds, if I remember correctly.
Okay.
And they had a fuel capacity of roughly 7,500 pounds of fuel, I believe. So over that, I can't remember the range, unfortunately, that the originally released was.
If the system is noticeably lighter in terms of the weight of the ramjet plus the weight of the fuel required to complete the mission relative to the J79 and its fuel consumption, that would be a large selling point. I had a couple of questions on the materials. The first was on the installation of the solid rocket motor. Slide 25 or something.
Nozzle installation.
Nozzle installation, yes. You took the higher thermal conductivity material for installation. Did that come with a substantial weight penalty?
Lauren, would you like to answer this question?
The weight penalty that we do experience, if we were to pick the graphite phenolic, it would weigh less, but since it's such a small area that we will need this insulation, we decided that the weight was, it was an alright trade-off.
Okay, because the carbon-carbon to make the much higher conductivity work, you're going to require quite a bit more of it.
Right.
And I was just wondering whether that trade-off was looked at in terms of the design at all.
So the throat area at the beginning is with the full amount of insulation that we will have. What we mainly looked at was the erosion rate, because comparing these two, the graphite phenolic would erode much faster over our burn time, so our area ratio would be changing. So we wanted to keep that as steady as possible. This is also why we went with the aluminum with a higher melting point for the thermal conductivity
Okay.
as that trade-off.
Okay, that was one thing that was not, when you're talking about insulation, saying, okay, we're going to pick the high conductivity material.
Right.
That was confusion there. The other question that I had was on the nozzle. You indicate that the nozzle wall temperature, that's like 30, somewhere around there. Nozzle wall temperature.
The ramjet nozzle or the?
Ramjet
Oh,
nozzle.
ramjet.
Oh, okay, that's a ways down.
Yeah.
So 50s on.
Average exit.
The average, the one that's labeled, I think it's just that one. The maximum wall temperature is about 3,500 Rankine, and you say you're going to make that out of Haynes 188. Haynes 188 is has a melting temperature well under 3,500 Rankine. How are you planning on cooling the column?
This was in like the recommendations where we talked about doing regenerative cooling, possibly for the nozzle, as well as looking at other chrome coatings possibly, or maybe some transfer mechanisms. Kurt has anything to add to that?
The thermal barrier coating will slow the rate of heat input into the component, but if your mission time is 36 minutes with that ramjet on, the thermal barrier coating by itself will probably not be adequate to
Right.
keep the nozzle cool.
Yeah. That's like I said, why we had the regenerative cooling, because we did realize how hot it is there. It's something we have to look into.
Okay. One of the things that gotten used to over the years of looking at preliminary designs is some, at least hand calculations of the stresses would be on the component. Is any, which components do you do stress analysis on as well as thermal analysis?
Mostly just the nozzle, as far as thermal analysis, stresses.
Okay. With the Haynes 188, what temperature do you think you'll be able to tolerate for the stresses that you analyzed?
Currently, we researched it to be around 2,460 was the max operational temperature, and the wall temperature far exceeds this magnitude as of now. However, more research would have to be conducted into, or more research would have to be conducted to look into more materials or other materials that are more suitable for this job.
Okay.
To meet this temperature, this stress requirement.
Okay. That was the component that was most challenged in terms of being able to survive or anywhere close to a 36-minute mission.
Exactly.
I thought